Bismillahirrahmanirrahim. Bismillahirrahmanirrahim. Assalamu alaikum, dear students. In my last lecture, I introduced to you gravitation, and then I explained to you the difference between gravitation, gravity, why gravity is important, how the life would look like if there is no gravity. This is what you have all learned in my previous class. In this class, I will tell you that how we can measure the gravity, because you know physics mostly believe on measurement. If something is not measurable, there is no place for those things in physics. So we need to measure the gravitational force also. Now the gravitational force can be measured by using the law of gravitation. The law of gravitation explains the nature and the magnitude of the gravitational force that exists between two objects, between two bodies, whether the bodies are heavenly bodies, whether small or big, doesn't make any difference. But let me tell you a brief history about the law of gravitation first. The law of gravitation was first stated by Sir Isaac Newton in 1665, and much of his work was published in his famous book Principia Mathematica. In his law of gravitation, he explained about the magnitude of the gravitational force between two objects. Now one day he was thinking, while sitting in his orchid, he was thinking that why some objects, when we throw them, they fall towards the earth. For example, look at this marker which is in my hand. When I throw the marker, it falls on the earth. He looked at why those things fall on the earth, but he thought that why the moon is not falling onto the earth. And then he was thinking that how the planets moves around the sun. What makes them move around the sun? He was thinking all about them. That suddenly an April fall, an idea struck his mind about the gravitation, right? And he then further investigated all these things. And I'd like to write the physical statement of the law. According to the Newton is investigated that in this universe, every body attracts every other body with the force which magnitude is directly proportional to the product of their masses. And inversely proportional to the 2 of the distance between their centers. Newton discovered that everybody in this universe attracts every other body with a force which I explained to you in my previous class, that force called the gravitational force. He said that this gravitational force depends on two things. That gravitational force is directly proportional to the product of the masses of the two bodies, and that force is inversely proportional to the square of the distance between their centers. And I would like to explain to you the term distance between their centers. This is a very important class. This makes this force a kind of central force. Now what does this mean? What is the central force? You see there, for example, look at this marker. If I just place them very close together, and if I ask you a question, then what is the distance between these two markers? Definitely, you tell me that the distance between them is 0. And most probably I will tell you that no, this is not like the case or the situation in physics. Right? Even in the general perception, the distance between them indeed exists. And if you see, if I mark the center of this marker as you see this, and if I mark it this, then indeed these two objects, when we consider them as a point objects, they are separated to some distance. So this is very important that in order to apply the law of gravitation, first we would reduce the bodies to a point bodies, and then we will calculate the distance between their center. Right? So the center to center distance always matter. Now in order to explain the Newton's second law, the Newton law of gravitation mathematically, let us consider any two bodies. Let me have body of mass m1, and let I have another body of mass m2. It doesn't make any difference whether m1 is big or small, whether m2 is big or small, whether they are of the same size. It doesn't make any difference. Now let us mark the center of the two bodies. For example, this is the center of the body of mass m1, and this is the center of the body of mass m2. Usually the center of mass of the body is is needed to be found, because you know that it is not necessary that all the object must be regular shaped object. As you see, look in this diagram, these two objects are kind of spherical objects, so that is very easy to point out their centers. But it is not necessary. For example, let's say the object may be like this, then how another object might be like, for example, this one. You just see it might be like rectangle or like this. Then how will I then measure the distance between these two objects? So the center of mass is most important in this case, and you have learned about the center of mass in the previous chapter. I think in the chapter 4, your teacher might have told you about the center of mass. So we indeed need the center of mass in order to calculate the gravitational force between two objects. So if the distance between these two objects is d, then I label it as d, right? This is called what? This is called the center distance, right? This is the distance between the center of the two objects. If they are separated by some distance d, then according to the Newton's second law of motion, the force will be along the center joining these two objects. These two bodies, as you see, let us join the center of these two bodies. So the force will only act along where the force will only act along the center of these two bodies, the line of the center of these two bodies. The force will neither be from the top, it will neither be from the bottom. So look, this object will exert a force on this body. Their force will be like this. Right? This object will exert a force on this object like this one. I would like to label this force as F12. And I would like to label this force as F21. Now, what is this F12 force? This force, you can write it 1 on 2. What does this mean? That it is the force which the body 1 exert on the body 2. It is the force with which it tries to pull it towards itself, right? Towards the center. Then what will be this F21 force? F21 force, it is what? It is the force which the body 2 exerts on the body 1. Is it clear to you all? Oh, yes. The body 2 and the body 1. Now, I would like to tell you here also that these two forces still will be the same in magnitude, although they act on two different bodies. According to the Newton third law, even the Newton third law holds true here. That these two forces will be the same in magnitude and they will be different in direction. Right? Now, mathematically, in order to explain this force mathematically, this is the physical statement. For the mathematical statement, as I already told you, let us see how we can explain this mathematically also. Mathematically, we can write the Newton law of gravitation as he explained that the gravitational force, if I denote the gravitational force by Fg, according to him, this gravitational force is directly proportional to the product of the masses of the two bodies. This is known as the law of product. This is the first part. It is directly proportional to the product of the masses of the two bodies. Now at this point I want to tell you that the gravitational force, it does not depend on the magnitude of the gravitational force does not depend on the mass of single body, although it must be clear to you, as I told you in my previous class, that gravity or gravitation is the intrinsic property of every mass. Every mass has gravity. But the magnitude of that force, it depends on the product of the two bodies. For example, let me explain you that if you have this mass, let us suppose for example, if you have this force M1, for example this mass M1 say 10 kilogram, and if you have the mass for example M2, and if you have 800 kilogram, now you just see, look at the board, they you see, look at the board. What is the ratio? The mass in one is 10 times bigger than what? Than the mass m2. But if I ask you a question that which body exert more gravitational force on which body, so usually sometimes much of the students of your level, they say that since it has more mass, so it has more gravity, and it will exert more gravitational force on this, and this will exert less gravitational force on this. So it is not the case. It does not depend. It depends on the product. Both will exert the same force on each other. The body in one will the force that exerts on one is the same as the force that exerts 2 on one and 1 on 2. Right? So the magnitude of the force is the same for both the bodies. So it does not depend on one body rather, it depends on the product of the two. Right? The second part of the law of gravitation is the inverse square law, 1 over v square. This is the inverse square law part. This is our equation number 2, as you see. Now look here. What this shows you that the force of gravity between the two bodies is inversely proportional to the square of the distance between their centers. Right? Now what does this mean? This means that if you double the distance between the two bodies, then the force will decrease 4 times. If you reduce the distance between the two objects, the force will increase 4 times. If you increase the distance between the two objects, if you pull them apart by the distance 3 times, then what will happen? The force will decrease 9 times. If you bring them close 3 times the distance as it was exist before between them, then the force will increase 9 times. Now, as I told you earlier, that if you just see, I told you that the distance, the center-center distance is important. Now, you know why I told you that the center-center distance is important. Because you know that, look, see here. It is important because of this fact. Now look, see here. It is very interesting. You know there is a gravitational force between them. They are in my hand, and you know I can easily remove them far apart. If it were not the case, if I just say that the distance between these two objects is 0, if I consider it 0, then what will happen? Something divided by 0, and definitely the answer will be infinity. What does this mean? That the force is infinitely large. Then will your teacher be able to remove them? Certainly not. The answer is a big no. Now, you see how is it easy for me that I can separate them. If the distance were to be 0, the force would be infinite, and your teacher would be unable to separate them. It will be a very huge infinite force, and for the two markers to be separated, it will be very, very difficult. So this is one of the reasons that the distance is between the object is always center to center. Right? So let us combine these two equations into a single equation. This is m1, this is m2, and you see it is inversely proportional to d square. And let me make it like this fg. If I remove the proportionality sign, it will be replaced by an equation sign and a constant, and then I'll be writing it like this, and then this will be the required equation which will measure the force that exists between two masses. Alright? So you see, look at this thing. Now what is this G? This G is known as what? This is known as the gravitational constant. And now I want to explain this G to you. This G is what? It is called the gravitational constant. Sometimes we call this universal gravitational constant. And this universal gravitational constant, it has the value the value of this G is equal to 6.673 into 10 raised to the power minus 11 Newton meter square per kilogram square. And I would like to write it in this here. At this point, it will be 6.673 into 10 raised to the power minus 11. I just skip the units, and I would like to write this value like M1 and 2 because I want to explain that part to you, right? Like this one, you see. Now, this is known as the universal gravitational constant. The question is, where does this universal gravitational constant comes from? This is the bigger question, right? What is this thing? The universal gravitational constant, it was not like this, that Newton just wrote an equation and he placed this G there and he said that it has this value. No. Universal gravitational constant, wherever you see the constant of proportionality in an equation, the constant of proportionality cannot be explained by theories only. It must comes from an experiment, and this is experimentally calculated. Newton calculated this gravitational constant. This gravitational constant is calculated by what? By an experiment. It does not comes from theory. It can only comes from what? From experiment, right? And that is beyond the scope of your syllabus. It is not in your course that how to calculate the value of G. So when you move on to the senior classes, maybe inshallah you will learn it there, that how the value of G can be calculated. Now, I just want to explain some aspects of this gravitational constant. This is called the universal gravitational constant, right? Its value is the same everywhere. It is this value on the earth, it is this value in the space. Wherever you go, this value does not change, right? Remember class, I just want to tell you another thing also. You might have seen this thing also. 9.8 or 10 meter per second square. Remember, there is a big difference between these two. And what is the big difference between these two? You see that this is gravitational acceleration, while this is universal gravitational constant. In no way these two things are the same. It is constant everywhere. Wherever you go in this universe, you have the same value, this G. Everywhere, whenever you want to calculate the gravitational force between two objects. While this is gravitational acceleration, and you have learned about the gravitational acceleration in the chapter number 2, that its value may change, right? It may change with change in altitude, it may change from planet to planet, and you might have learned that it has a different value on the moon than on the earth. For example, on the moon, it is 6 times smaller than that of the earth. But this value, it is the same everywhere. It is the same on the moon, it is the same on the sun. Wherever you go, you will have this value the same. The second important point about this, that you see, look at this numerical value. How small is this value? Look, 10 raised to the power minus 11. This is a very small value. This is one of the reasons that it makes the gravitational force smaller. You can only see the effect of the gravitational force between astronomical objects, right? Between bigger objects, between bigger bodies. For example, look at this. When I throw this marker, you see the marker comes towards the earth. You see that because there is a gravitational force between the marker and the earth, and the earth tries to pull the marker towards the center. But look, this is also masses. You see, look, aren't they masses? They are also masses. You see, look. Now why they don't attract each other? What is the reason? They both fall towards the earth, and they are not attracting each other. What does this mean? That there is no gravity between them? No. Certainly the answer is not this. What is the answer? The answer is this numerical value. Their numerical value is so small, right, that this makes this gravitational force very small. Right? For example, look at what would be the masses. Maybe this might be 15 gram or 20 gram. I will write 20 gram and 20 gram. So if you just convert them into the kilogram, let's say, so what will happen? 0.002 and 0.002, and when you multiply, what would be the distance between them? Very small. So what would be the force? The force would look like to be what? This force, for example, when I calculate the force between these two, it would be roughly, not the same, but roughly the same, 6.63, like something like that when you multiply the masses, and it will be 10 to the power minus 11, then force will be very small in magnitude, right? This is why it is not visible. This is why, if you compare this force with other forces, for example, if you compare the gravitational force with the electrostatic force, with the magnetic force, and with the nuclear force, you will find that this force is very weak, right? For example, let me, tell you that if you have some small pieces of the paper, this is one of your famous experiments. Let me try whether I'm successful or not. Okay, and when you look, this is already sticking to my finger. Is it happening? Yes. You just see when you rub the marker or the pen, this is the most common experiment in all the kids, and you see they all, look, they will all pulse towards the marker. You have seen that. So which kind of force exists between them? So you see the force between them is in fact the electrostatic force. And this electrostatic force is a very strong force. This is why the effect you see it is visible. Right? But in case of the marker, in this marker, if you want to look, for example, look at the gravity effect. Do you see, is this red marker pulls the blue marker towards itself? Answer is no. Why? Does it mean that there is no gravity? No. There exists the gravitational force between them. But what is the problem? This small value. It makes the force very small. This is why that force is not enough to cause acceleration in this object, in this marker. It is not good. But look, if you just want to try this thing on the earth, see, when I release, and you see, the sooner I release, and the sooner it will reach over that. Why? Because you have seen, earth has a very huge mass, right? While the marker, it has even a very small mass. But look, the huge mass compensates for that small value, right? And the earth mass, if you see the mass of the earth, which you know is rather 6 into 10 to the power 24 kg. So they make this force very bigger, and it causes acceleration in this marker. And you see that the marker is moving towards what? Towards the earth. But now let us just see. The question is it the marker also trying to pull the earth towards itself? The answer is yes. A big yes. If the earth pulls the marker towards itself, then the marker tries to pull the earth towards itself also. And these two forces, as they exert the same forces on each other, and these two forces are the same in magnitude. They are opposite in direction. But the problem is that we see the marker moving towards the earth, but we do not see the earth moving towards the marker. And of course, why? Because that you also know that acceleration is inversely proportional to mass. This is your Newton's second law, which you studied in the previous chapter. So you see, the earth has a huge mass, very big mass. So the same force produces less acceleration in the earth. But look at the marker. The marker has very small mass, and the same force produces very huge acceleration in it. So this is one of the reasons then the marker falls towards the earth, while the earth does not seems to move towards what? To move towards the marker. Now you see, look. So as I was explaining to you about something about the numerical value, so then numerical value actually do what? Then numerical value cause what? They cause the force of gravity to be very smaller between the ordinary object. So thanks God that this is. Why? Because if this value is to be very much bigger, as you have seen my just recent experiment in which a small pieces of the paper was small pieces of the paper were attracted towards the marker when I rubbed the marker against my hair. So now look, if this value were large, what will happen? Your teacher, when he was supposed to write on the board, for example, if I was supposed to write on the board, what will happen? The marker would stick to the board, and it would be very difficult for me to remove the marker from the board. So there is one of the difficulty I would face. We would stick to each other maybe, and it will be very difficult for me. A lot of force would be required to walk comfortably on the ground or on the floor. Why? Because if it would be greater, then between those smaller masses, the force would be even much more larger, and it would be very difficult for me. We will all stick together, right? So thanks God that this is smaller, right? So the ordinary masses, the smaller masses, then are convenient to him, right? So the second, how to calculate why the unit of this gravitational constant is Newton meter square per kilogram square, because if you just see, look here, then how I can manage this G, look, this D square here it is divided, there it will be multiplied, as you see, FGD square, and then M1 and M2. So now definitely you know that apart from the numerical value, as I told you, that the numerical value you see how I can just find the units for this G. Look, what is this? This will be Fg, and it will be D square, and it will be M1, and it will be what? M2. Now you see, class, look, apart from the numerical value, as I told you, it can only be determined by the experiment. We cannot do this thing, right? So you see, look, what is going to happen? That see that look, this will, what is the unit of force? Newton. What is the unit of distance? Meter. So you have meter square. And what is the unit of mass? Kilogram and kilogram. So kilogram square. So when you take it here, it will be like this. So this is why the unit of this G is Newton meter square per kilogram square. Now let us calculate the force. For example, you just see, look at this thing here. If you have two objects which are 1 kilogram, for example, if you just see, look, if I just solve it here, for example, if I just place, look, 6.673 Newton, sorry, 10 to the power minus 11 Newton meter square per kilogram square. So you see, if I have 1 kilogram mass, another mass is also 1 kilogram, as you see, and if the two masses are separated by distance of 1 meter square. So now you see with which force they will push apart on each other. This will get cancelled with this. This will get cancelled with this and this. And what do you see here? 6.673 into 10 to the power minus 11 Newton. So look at this force. How small is this force? Very small. Most probably not that much measurable. Right? By ordinary method. So you see that, look, this is how the value of G small, and it makes other things small. Now let me tell you about some of the properties now of this force. Properties of this gravitational force. I will just write some of the important properties. First of all, let me write the equation for the gravitational force. Our gravitational force is like this one. G, it is m1 m2 md square. Properties of gravitational force. Properties of gravitational force. First of all, the first property. This force, it is one of the fundamental force. Fundamental or basic force. It means that the nature needs this force for its survival. The universe needs this force. So it is one of the fundamental force which exists between bodies as big as the heavenly bodies, and it exists between bodies as small as on the atomic or the subatomic scale. So it is between our kind of masses. It is attractive only. It is what? It is attractive only. This force is attractive only. Right? This force is what? Attractive only. There is no repulsion. It only attracts each other. Pulling force it is. This force is, it is a central force. A central force means that a central force means that it only acts along the line joining the center of the bodies. Remember, so this is why it makes this force as a central force. The second important force, that it is important property, that it is medium independent. Right? It is what? This force is medium independent. This means that whatever is the medium between the two objects, it is not going to affect the strength of the force between them, because you have seen that this G is universal constant. So if it is not changing by any property of the medium, and masses are already the same there, so the force is not going to change. And the second important point, the next important point is that it obeys inverse square law. Yeah, it depends. It depends on the product of masses. Right? The force between two objects always depends on the product of their masses. Right? It does not depend on the individual mass. For example, as I told you, that if it is 100 and if it is 10, then the force of gravity will remain the same. They will be pulling each other with the same force. The next important point, that it obeys the inverse square law. Right? Then the force varies with the inverse square law. If you double the distance between them, the force, if you double the distance between the two bodies, the force decreases by 2 times. If you decrease the distance between them, the force increases by 4 times. So these are the this is one of the fundamental, also called the niche. Right? There is the next important point, the gravity. It is the intrinsic property of all the object. It is associated with every object. So this was our today lecture. Hope you have got all my points, and inshallah the assignment I will discuss with you on the Zoom.